Continuity. Let f be a function whose domain includes an open interval centered at a. Then f is said to be continuous at a if the limit as x approaches a of f of x exists and equals f of a. In other words, limit equals value at a. Example. Suppose we have the function f whose graph is shown here. We'll observe that f is continuous everywhere except at x equals -1, 0, and 2. F is not continuous at -1 because the limit as x approaches -1 is equal to 1, while the value of the function at -1 is equal to 2. F is not continuous at 0 because its limit as x approaches 0 does not exist. F is not continuous at 2 because f of 2 is undefined. Notice that its limit there does exist, it equals -1. There are three types of simple discontinuities. The function shown here exhibits each of these three types. This function has a jump discontinuity at -1. There, each of the one-sided limits exists, but the limit does not exist because the one-sided limits are different. The function has an infinite discontinuity at x equals 0. Infinite discontinuities are associated with vertical asymptotes, which occur when at least one of the one-sided limits is plus or minus infinity. At x equal to 1, this function has a removable discontinuity. Here the limit exists but does not equal the value of the function. In this particular case, the function is undefined, but the same thing would be true if it were defined to be anything other than the limit as x approaches 1. If the function's value at 1 were 2, then the hole in the graph would be filled in and the function would become continuous. This is why we refer to this type of discontinuity as removable. Recall that if p of x is a polynomial and a is any real number, then the limit as x approaches a of p of x is equal to p of a. We can now state this basic fact in a different way. It simply says that polynomials are continuous everywhere. Also recall that if p of x and q of x are polynomials and q of a is not 0, then the limit as x approaches a of the rational function p of x divided by q of x is equal to p of a divided by q of a. In other words, limit equals value for any rational function and any a where q of a is not 0. We can state this in terms of continuity as follows. Rational functions are continuous wherever they are defined. This is the graph of a garden variety rational function. Notice that the denominator is 0 at two different places, at x equal to 0 and x equals 1. At x equal to 0, it has an infinite discontinuity, essentially because the x factor in the denominator cannot be canceled out. At x equal to 1, it has a removable discontinuity, because simplification removes the x minus 1 factor from the denominator. Also recall that for all real numbers a, the limit as x approaches a of sine x equals sine a, and the limit as x approaches a of cosine x equals cosine a. In other words, sine and cosine are continuous everywhere. Also recall that if a is not an odd multiple of pi over 2, then the limit as x approaches a of tangent x equals tangent a, and the limit as x approaches a of secant x equals secant a. And if a is not a multiple of pi, then the limit as x approaches a of cotangent x equals cotangent a, and the limit as x approaches a of cosecant x equals cosecant a. We can phrase all of this in terms of continuity by simply saying that tangent, cotangent, secant, and cosecant are continuous wherever they are defined. Several properties of continuous functions follow directly from properties of limits. Let's first recall the following. If the limit as x approaches a of f of x and the limit as x approaches a of g of x each exists, then the limit of the sum or difference equals the sum or difference of the limits as x approaches a. The limit as x approaches a of a constant times f of x equals the constant times the limit as x approaches a of f of x. The limit of a product is equal to the product of the limits, provided each of those limits exists. If the limit as x approaches a of g of x is not equal to 0, then the limit as x approaches a of the quotient f of x divided by g of x is equal to the quotient of the limits. Now here are corresponding statements about continuity. If f and g are both continuous at A, then f plus g and f minus g are both continuous at A. Any constant times f is continuous at A. F times g is continuous at A. And if g of A is not 0, then the quotient f divided by g is continuous at A. Compositions. Here's a fact about limits of compositions. If the limit as x approaches a of g of x equals b, and if the limit as x approaches b of f of x equals c, then the limit as x approaches a of f of g of x equals c. This is equivalent to saying that if g is continuous at a, and if f is continuous at g of a, then f composed with g is continuous at a. Example. Let f of x equal 3x squared plus x squared minus 1 divided by x minus 1 times x minus sine x. At what values of x is f not continuous, and of what type is each of its discontinuities? Let's first observe that 3x squared minus 1, and the denominator x minus 1 times x minus sine x are each continuous everywhere, since they involve only polynomials and the sine function. Therefore, f is continuous wherever the denominator in the second term is not 0. That is, wherever x minus 1 times x minus sine x is not 0. Now x minus 1 is 0 when x is 1, and x minus sine x is equal to 0 only when x is equal to 0. You can see this easily from the graphs of x and sine x. The only point of intersection is the origin. So f is continuous everywhere except x equals 1 and x equals 0. To determine the type of discontinuity at x equals 1, we'll examine the limit as x approaches 1 of f of x. The numerator in the second term factors into x plus 1 times x minus 1, and so the x minus 1 factor cancels, and we conclude that the function f of x equals 3x squared plus x plus 1 divided by x minus sine x for all x other than 1. So the limit exists. In fact, the limit as x approaches 1 of f of x is equal to 3 plus 2 divided by 1 minus the sine of 1, which is approximately 15.616. Therefore, the discontinuity at x equals 1 is removable, corresponding to a hole in the graph of f. To determine the type of discontinuity at x equals 0, we first notice that the limit as x approaches 0 of f of x does not exist, because the numerator in the second term approaches negative 1, while the denominator approaches 0. And in fact, the limit as x approaches 0 from the left of f of x is equal to negative infinity. This is because when x is close to 0, x minus 1 and x squared minus 1 are both negative, and if x is slightly less than 0, then x minus sine x is also negative, because for negative values of x, sine x is greater than x. Again, this is apparent from the graphs of sine x and x. Also, the limit as x approaches 0 from the right of f of x is equal to plus infinity, because when x is close to 0, x minus 1 and x squared minus 1 are both negative, but when x is positive, x is greater than sine x, and so x minus sine x is positive. Therefore, f has an infinite discontinuity at x equals 0, corresponding to a vertical asymptote. Here's the graph of f. Notice the vertical asymptote and the hole at x equals 1. Example. Find numbers a and b so that the following function is continuous everywhere. F of x equals a times x if x is less than minus 1, x squared plus a minus b if x is greater than or equal to minus 1 and less than 1, and b times x if x is greater than or equal to 1. Since the parts of f are polynomials, we only need to choose a and b so that f is continuous at minus 1 and 1. In order for f to be continuous at minus 1, we want the limit as x approaches minus 1 to exist, which requires that the two one-sided limits exist and be equal. And we also want that common value to be the same as the value of the function at minus 1. The limit as x approaches minus 1 from the left of f of x is equal to the limit as x approaches minus 1 from the left of ax. The limit as x approaches minus 1 from the right of f of x is equal to the limit as x approaches minus 1 from the right of x squared plus a minus b. The limit as x approaches minus 1 from the left of ax is equal to minus a, and the limit as x approaches minus 1 from the right of x squared plus a minus b is equal to 1 plus a minus b. Notice that the value of the function at minus 1 is also 1 plus a minus b, so we automatically have the right-sided limit equaling the function value here. So we have an equation involving a and b. Minus 2a plus b equals 1. Now let's look at x equal to 1. We want the left-sided limit as x approaches 1 to equal the right-sided limit as x approaches 1, and we want each of those limits to equal f of 1. F of 1 is equal to b, and that equals the limit as x approaches 1 from the right of b times x. So now we only need for the left-sided limit as x approaches 1 to equal b. That left-sided limit is 1 plus a minus b. So we have a second equation involving a and b. A minus 2b equals minus 1. So now our problem is that of solving a pair of equations for two unknowns. Here we'll multiply the second equation by 2, and then add the two equations together to eliminate the a term, and we find that minus 3b is equal to minus 1. So b equals 1/3. Now that we know b, we can go to either of the two original equations to find a. Using a minus 2b equals minus 1, we substitute in b equals 1/3, and then solve for a. This gives us a equal to minus 1/3. Now here's the function we found, along with its graph. Notice the continuity at plus and minus 1. Compositions. As we stated previously, if g is continuous at a, and if f is continuous at g of a, then f composed with g is continuous at a. Now let's look at an example to illustrate this. Let f of x equal x divided by the absolute value of x. The value of this function is minus 1 whenever x is less than 0, and plus 1 whenever x is greater than 0. The graph of f looks like this. Notice that f is continuous except at x equals 0, where it's undefined and has a jump discontinuity, since the one-sided limits exist there but have different values. Now, if we compose f with sine, then we have the function sine x divided by the absolute value of sine x, and this function will be continuous wherever sine x is not 0. That is, wherever the value of sine x is not equal to the number where f is discontinuous. Now sine x is equal to 0 at multiples of pi, so f of sine x is continuous except at multiples of pi. At multiples of pi, the function is undefined and has a jump discontinuity just as f did at 0. In fact, the graph of the function looks like this. One-sided continuity. If the domain of f includes an interval whose right endpoint is a, then f is left continuous at a if the limit as x approaches a from the left of f of x is equal to f of a. If the domain of f includes an interval whose left endpoint is a, then f is right continuous at a if the limit as x approaches a from the right of f of x is equal to f of a. Here's the graph of a function that illustrates left and right continuity. Notice that the function is discontinuous at x equals 0 and x equals 2. The function is right continuous at x equals 0 since the value of the function there is the same as the right-sided limit. The function is left continuous at 2 since the value of the function there is equal to the left-sided limit. Now let's note that a function f is continuous at a if and only if it is both left and right continuous at a. Example. We know that the limit as x approaches a of the square root of x is equal to the square root of a for all positive a, and that the limit as x approaches 0 from the right of the square root of x is equal to 0. So the square root function is continuous at every positive number, and it's right continuous at 0. Continuity on an interval. Let I be an interval. It may be a closed interval, an open interval, a half-open interval, or even an unbounded interval. A function f whose domain includes I is said to be continuous on I if for every number c in I, f is continuous at c if c is not an endpoint of I, f is right continuous at c if c is a left endpoint of I, and f is left continuous at c if c is a right endpoint of I. If the domain of f is an interval, and if f is continuous on that interval, then we may simply say that f is a continuous function. For instance, f of x equals 1 over x is continuous on the interval 0 to infinity and on the interval minus infinity to 0. The square root function is continuous on the closed interval 0 to infinity. Notice that this interval has a left endpoint and that f is right continuous there, since the value of the function is equal to the right-sided limit. F of x equal to the square root of 1 minus x squared, whose graph is the top half of the unit circle, is continuous on the closed interval minus 1 to 1. Notice that at minus 1, the value of the function as well as the right-sided limit are both 0, and at 1, the value of the function and the left-sided limit are both 0. So the function is right continuous at the left endpoint and left continuous at the right endpoint. We briefly mention here two consequences of continuity. First, the intermediate value theorem. Suppose that f is continuous on a closed bounded interval ab. Then for each number k between f of a and f of b, there exists a number c in the interval ab where f of c is equal to k. In other words, the function takes on every intermediate value between its endpoint values. A corollary to this is useful for finding zeros of functions. If f is continuous on the closed interval ab, and if f of a and f of b have opposite signs, then there exists a number c in the open interval ab where f of c is equal to 0. This is actually just a special case of the intermediate value theorem where k is equal to 0. Notice that there's no guarantee that there's only one such c. In fact, there could be any number of solutions of f of x equals 0 in an interval where the endpoint values have opposite signs. Example. Consider the polynomial f of x equal to x cubed minus x squared plus 5x minus 2. The value of f at 0 is minus 2, and the value at 1 is 3. Since polynomials are continuous, it follows that f of x is equal to 0 for some x between 0 and 1. And this is in fact the case, as we can see from the graph of f. The extreme value theorem states another important property of continuous functions. Suppose that f is continuous on a closed bounded interval ab. Then there exist numbers c and d in the interval ab such that f of x is greater than or equal to f of c and less than or equal to f of d for all x in ab. The number f of c is the minimum value of f on the interval ab, and the number f of d is the maximum value of f on the interval ab. So the theorem basically says that a continuous function on a closed bounded interval takes on both a minimum value and a maximum value on the interval. A couple of remarks about the hypotheses of the theorem. This picture shows the graph of a function that's continuous on the open interval 0, 1. It has no minimum value and it has no maximum value. This shows that the hypothesis that the function be continuous on a closed interval is necessary in the theorem. Here, f is defined but not continuous on the closed bounded interval 0, 1. Its maximum value is 1, but it has no minimum value. Thus, the continuity hypothesis is also a necessary one in the theorem. Finally, we make note of a trivial case. Here, f is a constant function. Its maximum value and its minimum value are the same, and that value is attained at every point in the interval. This example indicates that in the extreme value theorem above, there may be many such numbers c and d in the interval. A method for finding extreme values of functions will be highlighted later in the course.